Good morning, everyone. So what I would like to do in the next 45 minutes or so is to take you through a tour in the heart of matter, at the center of atoms, where nuclei reside. And I would like to explain you how we compute properties of nuclei, and that's why I gave it this title. What you see here is an artistic visualization of what you're actually doing. So you see a nucleus made by protons and neutrons, and each of these nucleons have a bunch of numbers on top of it, because eventually when we put everything in the computer, everything becomes bits. So that's kind of to give you an idea of what we are doing. But let's take it from the very beginning. So we are physicists, and what we would like to do is to understand the building blocks of matter, right? And the way we do it is by probing matter with different wavelengths. And as we increase the momentum of our wavelength, we look at smaller distances. So you can imagine this, of course, as light or also as a particle. And what we know is that water, which we are all made of, is made by molecules. The molecules themselves are made by atoms, which are absolutely not these indivisible particles that the ancient Greeks thought they would be when they introduced them, but they are made by electrons orbiting the nucleus. The nucleus itself is made by a collection of interacting protons and neutrons, which we call nucleons, and they are themselves made in terms of quarks and gluons. And this is where we reach the fundamental level. Now, I'm going to be concerned with this kind of picture, and if we want to put a scale here, we are going to talk about lengths of the order of 10 to the minus 15 meter, also called femtometer. And the energy scale typical of the system is of the order of MeV, but you can have very heavy nuclei which have excitation energies that are of the order of just electron volt. And you may want to probe your nucleus also with energy of the order of a few hundred of MeV. So this is more or less the energy regime we are talking about. So nuclear physics per se is quite an old science. It's more than 100 years old, because I think what sets the birth of nuclear physics is the famous experiment of Rutherford. He was doing a scattering experiment with alpha particles, which are helium-4 nuclei, so just made by 2 protons and 2 neutrons. And he was shooting them on very thin gold foil. And he observed that most of the time this alpha particle would go through unperturbed, but sometimes it would bounce back at large scattering angle, meaning it was due to a scattering with something very hard, where all the matter is concentrated at the center of the atom, and that is the nucleus. And if you read his words, he's talking about scatter encounter, and that is, in modern language, the nucleus. Of course, since then we have learned a lot, and one way to represent at least part of what we know is to do this plot, which is called the chart of nuclides. You have one here too, because this is a Kern Physics Institute. And so what is that? This is that a two-dimensional plot with a neutron number on the x-axis and proton number on the y-axis, where every point that you see here is a nucleus. So we know, let's say, roughly 300 of them, which are stable, meaning we have not seen them decay. And those are the black points here in the middle. All the other colored points that you see there are nuclei that we know exist, but are somehow decaying in one way or another back to stability. So many of them are unstable nuclei, and we know roughly 3,000 of them. But we expect there to be many more, a few thousand more, and they are expected to be in this so-called terra incognita, so where this shaded area is mostly in the neutron-rich part. And these nuclei are so short-lived that they have been formed, they are formed at some point in some stellar environment, but then they decay shortly after, and we cannot find them on Earth anymore. So the way to study them is to produce them synthetically in the laboratory. And for example, you would do that at the so-called radioactive beam facilities. The closest one to here would be GSI Fair. Or you can also, of course, rely on theoretical prediction on that, and that's where I want to go because I'm a theorist. So let's talk about what the goal is of nuclear theory. So we would like to develop a unified theory for all nuclei across the nuclear chart. But not only that, because we would like to connect the picture of the nucleus as a system of interacting protons and neutrons as much as possible to the fundamental theory of QCD. And on the other hand, we also would like to connect to astrophysics, where there is a lot of nuclear physics input that we need to understand astrophysical phenomena. So this is, of course, doing all of these is an ambitious goal. We are not yet there, but we are in a good position. And let's say if you wanted to achieve all of what I try to say with this picture, we have to face some challenges. I would like to now give names to these challenges and then go through them a little bit more in detail, one by one. So first, there is a so-called interaction challenge, which has to deal with how we connect nuclei, so nuclear forces, or the forces that bind the nucleus, to QCD, to the fundamental level. If we have a way to model our force, the next challenge we encounter is a many-body challenge, because we have to be able to describe many nucleons interacting with one another, and we want to see if we are able to describe the properties of the nucleus in that, starting from that force. And last but not least, we have also these astrophysical challenges. As I said already, there is a lot of nuclear physics that really determines the astrophysical phenomena. For example, the properties of neutron stars, we'll come back to that, or if we wanted to understand how the chemical elements were formed, there is a lot of nuclear physics that goes in there. So these are the three main challenges. Now I would like to go through them one by one. So let's talk about the interaction challenge. As you know, theorists like to explain the infinitely ranged Coulomb force between two electrons as being mediated by the exchange of a photon, which is mass zero particle. You can build an analogy and try to explain the nuclear force, the force between two nucleons, which is short range, via the exchange of a massive particle this time, with the mass of the particle being inverse proportional to the range of the force. That is what Yukawa did, and he actually, knowing the range of the force, he was able to predict the mass of the particle to be exchanged, which is roughly 140, which was later discovered to be the pion. So this diagram here is called the one pion exchange. Is still at the basis of most of the modern potentials to describe nuclear force. So of course so this was 1949, we moved a lot beyond that. And I can say that for a long time there were two main ways to derive potentials. For NN means for nucleon-nucleon. We would call a potential realistic in our field if we are able with that potential to describe nucleon-nucleon scattering data with a chi-square per datum equal 1. We are talking about thousands of data here. There are really very good data. And there were two main ways to do that. One, which we would call a phenomenological model. So you can kind of make an ansatz here, a functional form, based on some guiding principle, and then you fit parameters. Another way would be to generalize this one pion exchange to the one boson exchange. Instead of exchanging only a pion, you can exchange other kind of mesons.
So what did you say is chi?
Sorry?
What did you say is chi?
Chi square is the fit to the data. So you have thousands of nucleon-nucleon data, scattering data, taken at various labs, and you want this to be reproduced by your theory, and we are able to do that with chi-square per datum of the order of 1, 1.2, depending on the various potentials. I will show you later a figure where maybe it is more clear. Let me say, though, that this is probably, these two methods are still used, but it's belonging more to the past, because the new kid on the block is the Chiral effective field theory, which is a way we have to connect nuclear potentials as much as possible to the fundamental theory of QCD. So this is not that new also, it's at least 20 years that we do that, but I think in the last 10 years or 5 years it has really become a trend. Every nuclear theorist in my field is using this kind of method. So let me try to explain briefly. So if you started from the fundamental degrees of freedom, like quarks and gluons, you would have this Lagrangian here. And if you looked at it in the limit of vanishing quark masses, this Lagrangian has a symmetry, the chiral symmetry, which is then broken explicitly due to this mass term, but also spontaneously. And then you know that Weinberg and other people have taught us that you can change your degrees of freedom and use effective ones, which in our case would be the protons, the neutrons, and the pions. And as long as you construct your theory which is compatible with the symmetry of the fundamental theory, then you should be fine. That's exactly what we are doing. So we construct Lagrangians for the pure mesonic sector, for the meson and nucleon sector, or the only nucleonic sector that are compatible with the explicit and spontaneous chiral symmetry breaking. In nuclear physics, this is the most important part, the nucleonic part, which has led to, thanks to the work of many people, to this kind of list of Feynman diagrams that represent the nuclear force. Let me go through these a little bit more detail. So first of all, you see that this is kind of a matrix. We have columns with 2 nucleon forces, but also we have 3 and 4 nucleon forces. And on the rows, we have a categorization based on the importance of each of these Feynman diagrams. Of course, you can construct infinite many terms that satisfy the chiral symmetry, but then you would be back to the problem of before. You cannot solve it. You have to have a way to say what is more important and what is not. And this is done via something called power counting. So, for example, if you look at the leading order, we see it here. So the lines are the nucleons, the dashed lines are the pions. We see again our 1 pion exchange, but then we also have a contact term. So this is the case where the 2 nucleons are basically on top of each other. That contains information about high energy physics, which is not given by the chiral symmetry directly. If you go to the next leading order, you start to see 2 pion exchanges and so on and so forth. And the nice thing of this is that you see a hierarchy, that the 3 nucleon forces are coming at subleading order. So they are less important than the 2-body force. And the 4-body forces are even less important. And that is very important because including these diagrams here, it's a much harder task than just doing the 2 nucleon forces. So this is a very systematic approach, but it doesn't give you the values of the coupling constants in front of these contact terms. Those, at some point, they may come from QCD, from lattice QCD, for example. But at the moment, what we do is we ask experiment what the values of this coupling constant should be. And this goes back to the question of before. We have a lot of nucleon-nucleon scattering data. Here is one example in a partial wave. The one is 0-0. So what you could do is you take, for example, this column. You take your leading order, next leading order potential, you solve a Lippmann-Schwinger equation for 2 cis nucleons only. You calculate the phase shifts, and they will depend on some parameters which you then fit the data. And by the time you increase your Chiral order, you have enough parameters to fit that your theory then goes exactly on top of the data. So this is the N3LO, that's this maximum order here. You see it's a very nice description of the data. If you stop before, it's not so nice. And I could show you a bunch of other partial waves where the situation would be similar. So this is the way we calibrate two-body forces. And of course, yeah, I should have said, of course, any effective field theory works only if there is a separation of scale, right? And the separation of scale is explained here. So we are always having in mind, we want to study low energy properties of the nucleus. And the momentum scale we are interested in is this Q, which should be always smaller than a certain breakdown scale, which is the scale at which is not correct to consider nucleons as your degrees of freedom anymore. This is roughly 700 MeV or 1 GeV. So you have to look at properties of the nucleus at lower energies, but this is exactly where nuclear physics is, lower Q than 700 MeV. So we calibrate these two nucleon forces, but then also in the three nucleon forces here you have new low energy constants, which you need to calibrate also. You need at least 3-body nuclei to do that. And you can do that, of course. And once you have calibrated your Hamiltonian, you want to predict observables for the nuclei by doing a calculation. And there is no unique way of doing this feat. That's why you don't have one nuclear force, but you can construct families of nuclear forces. And that's very important. It's not only one potential, but there are families. So once you have this interaction from Chiral effective field theory, you have to solve the many-body problem, which is your next challenge. Yeah. And what is shown here is this a picture that shows again the chart of nuclides underneath here with this stable nuclei in black. And above this shaded area describe the three main methods to solve the many-body problem in nuclear physics. The red area here is the regime of the so-called Ab Initio methods. I will tell you more about those because those are exactly the methods I use. They are the most accurate, the most sophisticated one. The green part is the regime of the so-called shell model, or also configuration interaction. And the light blue here extends further down. It's the regime of density functional theory, which is based on mean field approximation. So generally speaking, you go from being more accurate and precise and including all the correlations here and into increasing the number of approximation and going to mean field as your number of particles increases. And that's kind of obvious because as the number of particles increases, your problem becomes more and more difficult to solve. The important thing is that this shaded area overlap, and there is where we want to compare the methods. And that's why I've highlighted here calcium-48, because I will show you an example of calcium-48 later. The idea is to develop a unified theory of nuclei, and by the fact that you see this patchwork now, you see that we are not yet there. But our goal is really to take this red shaded area here and expand it out to cover the whole nuclear chart. And we've done quite some progress in that respect. So last challenge is in astrophysics, where the theory is very important. For example, if you want to know the nature of neutron stars, you would need to talk about something like the equation of state, which depends on the way the nucleons interact. If, for example, could derive an equation or calculate an equation of state from the current interactions I mentioned before. Or, let's say you wanted to know about the nucleosynthesis of elements. The light elements are formed in Big Bang nucleosynthesis or in stellar environments. You need to know cross-sections at very, very low energies, where it's very difficult to measure. So you need to rely on theory there too. Or if you wanted to know how the very heavy elements were formed beyond iron, they are formed in either supernova or neutron star mergers. There, what you need to know are masses of very exotic nuclei, reaction rates. These nuclei that are involved there are so exotic that we didn't measure them yet at the labs. So you need to rely on theory. So theory plays an important role in this realm too. Okay, now let me tell you a bit more about the Ab Initio nuclear theory. So, Ab Initio, it's Latin word which is used in many different areas of physics with different meaning. Here, what I mean is that you start from neutrons and protons as your degrees of freedom, and you solve the non-relativistic quantum mechanical problem, basically, which means basically Schrödinger equation, this H psi E psi, where in your Hamiltonian you have, besides the kinetic energy, you have these 2 and 3 nucleon forces. In principle, you can have also 4 nucleon forces that are derived from chiral effective field theory. And then you solve this equation in an exact way, which doesn't mean analytical, because these potentials are so complicated, and even for 2 particles there is no analytical solution. It's always numerical. And if the solution is numerically exact, I would call this method an Ab Initio method. If you have to introduce approximation, sometimes you have to do, these approximations have to be controllable. So you have to have a way to reduce your theoretical uncertainty. So there are many methods that belong to this category, which we could all put into a magician hat. I'm going to take out only 2, just which are the 2 I work with, to give you a flavor of what it is, but I will not go into many details. So I pick at one which is more a few body method. Few body means light systems, let's say 3, 4, 5, 6, maybe 7, something like that, but not 200 nucleons. That is called hyperspherical harmonics. And then I will show you another one, which instead a real many-body method whose goal is to really do even at some point the heavy nuclei. That is called couple cluster theory. They have not much in common with each other, besides the fact that you need to solve the corresponding equations on high-performance computing, because otherwise you would be stuck. So we solve it on, for example, on the Morgan cluster that we have here in Mainz. So let me give you an idea of what it is. Hyperspherical harmonics are a special basis that you use to expand your wave function. You all know what spherical harmonics are, because you all have solved the hydrogen atom, right? So these hyperspherical harmonics are just the coupling of various spherical harmonics with some polynomials attached to it to describe an A-body nucleus. They can be constructed recursively. They have very nice convergence property. But for now, just see them as a basis you use to expand your wave function. And if you take these ansatz and plug it into the Schrödinger equation, what you would see is that you end up having to solve a diagonalization problem. You have to diagonalize your Hamiltonian on that. The fact is that this Hamiltonian matrix becomes larger and larger as you increase the number of nucleons. So, for example, if you have 3 nucleons, like let's say helium-3, you have something like 1,000 states. But if you go to do helium-6, you have 10 to the 6 states, which you would think is not big. Well, actually, it is big, because these matrices are dense, they are not sparse. The limit is 10 to the 7, where you could diagonalize efficiently these matrices. So while it is an exact method, and the drawback is that it has a bad computational scaling, it's kind of factorial. The number of states increase factorially, so you cannot do lead with this. But you can do 3, 4, up to maybe 8 particles very, very precisely. And it is exact because when you converge this expansion, you calculate, for example, the ground state energy, and you should see that it's independent on this cutoff that you put in your expansion. So that's when we call a calculation converged. Okay, this is for hyperspherical harmonics. For couple cluster theory, instead, the situation is different, because as I said, is a real many-body method. It is starting from a Slater determinant, which is this here. This is an uncorrelated state, which you can construct something from any single particle you want. And you imprint correlations with an exponential ansatz, e to the t. And this t is an operator which you expand that's in clusters, where your cluster are basically particle hole excitations. So suppose you do a mean field and you can fill a certain number of orbitals of single particle states. And then you construct particle hole excitation on top of it, 2 particle to hole, 3 particle to hole, etc. But so of course, if you do an A particle A hole truncation, it's not a truncation anymore. Actually, it's an exact theory. But this becomes too complicated. So what is done is that we truncate this operator T, for example, up to here, 2 particle to holes. That's called coupled cluster singles and doubles. So that's an approximation which you wouldn't like in principle, but there is a clear way how to improve your calculation, because you can put 3 particle 3 holes, which are called triples, and that is going to improve your calculation, and so on and so forth. So because this expansion is in the exponent, even if you truncate here, it's actually very close to the exact result. So the very good thing of this method is that the scaling, the computational scaling as a function of the mass number is polynomial. So of course it gets harder the heavier the nucleus it is, but it's not this factorial thing. So you can actually calculate much heavier nuclei, and this is what has allowed us to obtain this explosion in mass number. And this, you see, this is mass number that was reached by calculations as a function of time. And if, let's say, 10 years ago we were able to do just oxygen 16 particles, now we can do 100 particles. This is exploiting basically the better and better computers we have. Okay, so this is just a way to give you a flavor of what these methods are, with not too many details. But now I would like to narrow the scope down a little bit and focus on a specific class of nuclear properties that you can calculate with these methods, which are the electroweak properties of nuclei. So the question I'm interested to answer is, what happens if I take my nucleus and I put it in an electromagnetic field or in an electroweak field? How does it respond? And the quantity that encapsulates this information is this guy here, which is called the response function. It contains the expectation value of an operator O, which of course will depend on the probe you have. If you have a photon here or a neutrino, it will be different. But it's taken between the ground state and the excited state. And the typical shape of this response function is seen here. It can have quite a detailed structure that is a dynamical property of the nucleus. And while some features like this giant resonance are very common across the nuclear chart, the structure here is very nucleus dependent. So why are we interested in that? Well, of course, this is interesting per se in nuclear physics to calculate it and compare to experiment. But the reason why I wanted to mention this to you is that this allows to connect nuclear physics with other fields of physics where the nucleus plays an important role. And those are the examples I want to make to you. So it allows you to connect to atomic physics, to astrophysics, and to particle physics. And I will show you selected examples of these observables calculated with Ab Initio method that are connected to these other fields of physics. So let's start from atomic physics. So I'm going to tell you the story of the proton reduced puzzle, which you probably have heard. So it was a few years ago, in 2010, when the first experiment on muonic hydrogen lamp shift was performed. This is a spectroscopic experiment of an exotic atom where a proton is orbited by a muon instead of by an electron. Out of a measurement of the lamp shift, you can extract the charge radius, which tells you how big the proton is. And they've got this number, about 0.84, which is much smaller than what was previously measured in systems where the electron orbits a proton. The experiments were either hydrogen spectroscopy or electron scattering. And the difference was substantial. It's shown here. So here you have the results from the muonic atom measurements, muonic hydrogen, I should say. And here are the results from the electron-proton system. They were very different, 7 sigma deviation. That's quite significant, and that's what got everyone excited, because it could have been an indication that lepton universality is violated. So that is also the reason why I got excited into this, but I think right now the situation has evolved quite a bit. There are at least 2 new measurements on electronic systems, one of which gives a small radius and one of which gives a big radius. And there is also a third one which is not published yet, so I didn't put it, that gives yet again a small radius. So I would say that right now the situation seems more like there is a problem in understanding the systematics of the various experiments more than there is beyond standard model physics. Nevertheless, this is not yet solved. It's just an ongoing debate. And the collaboration that discovered this so-called proton radius puzzle in first place has decided to do other measurements in which instead of having a proton orbited by a muon, you have a light nucleus orbited by a muon. This is called a light muonic atom. What has been done already, measurements on muonic deuterium, they have been published a couple of years ago. Muonic helium-4, muonic helium-3 also have been measured, but they are not published yet. And what was the idea? The idea was to see if by measuring the length shift of these systems and extracting the charge radius, if you would see any differences with respect to ordinary atoms or electron scattering. Basically, if this puzzle has a dependence on Z or N, proton number or neutron number. That was the whole goal. Now, the fact is that the muon, because it is much heavier than the electron, it orbits much closer to the nucleus. So it is much more influenced by the nucleus than it is an electron. So how are the charge radii extracted in atomic physics? So what is measured is an energy difference between the 2s and the 2p state, that's the length shift. And that is related to the charge radius, which is what you want to extract by this formula. So the first part, the first correction there are called QED correction. They are very well known. The second and the third term are nuclear structure corrections that are much bigger in muonic atoms than they are in ordinary atoms. The first term is a finite size effect, and it comes from first order perturbation theory from on the Coulomb potential between the nucleus and the muon. We know that part very well. What we know much less well is this third piece, which is called two-photon exchange, that comes from second order perturbation theory, and it's represented by this Feynman diagram. So here you have the muon, here you have a nucleus. First a photon is absorbed and then is emitted. And in the intermediate lines here, you have all the possible excitations of the nucleus. So it's not so difficult to kind of imagine that this property here depends on the electromagnetic response function of the nucleus. So that's what we can calculate very well. And that's what we did to provide this number, which then is used by experimentalists. So I will show you two examples. So this is first muonic deuterium, where we have calculated this two-photon exchange for using chiral forces in an order-by-order expansion. Here you see leading order all the way up to N4LO, which is the highest order we can do today. And you see there are three different colors, which corresponds to the three different families of interactions. Because as I told you, there is no unique way to fit these low energy constants. There are various methods. But as you see, by the time you reach, let's say, the next to next reading order, everything is flat. And it doesn't move if you go to higher order, which means the chiral convergence is ensured. And you can see this as an uncertainty if you want. So this is what we did for the deuterium. The other example I wanted to show you is for muonic helium-4. So that's a slight 4 nucleons instead of 2. It's a bit more complicated. And what this plot shows you is that the use of Ab Initio Theory allowed us to reduce the uncertainty on this two-photon exchange part, which is a game changer for the experimentalist. The what you see here is the calculation as a function of years, if you want. So in the 70s, first these quantities were calculated and they were getting an estimate of the value, but there was no way to assess an uncertainty. Then people tried to give an uncertainty to this, mostly based on experimental data. And this is a very big uncertainty, which the experimentalists doing measuring atoms would not be happy with. And using Ab Initio methods, we were able to bring down this uncertainty by quite a bit. Okay, so this is what I wanted to show you regarding the connection to atomic physics. Now let me talk briefly about the connection to astrophysics. So as you all know, gravitational wave observation have not only seen the merging of two black holes, but also the merging of two neutron stars. And this is going to be very important for nuclear physics, because in the so-called multi-messenger era of astrophysics, we expect these measurements to provide new constraints on the so-called equation of state of nuclear matter. What is that? This is nothing else than basically the energy per particle of an infinite system where you have a slight unbalance between proton and neutron, that is this delta. And you can expand this delta in a Taylor expansion if you want. And then you can expand this coefficient in front around saturation density. And you introduce some parameters, which are parameters that determine if an equation of state is soft or hard, which eventually has also impact on whether a neutron star can exist with a large radius or a small radius. So the gravitational waves will provide us with stringent constraint on these properties. But this is not the only way to do that. You can actually, or you should actually, combine the constraint from gravitational waves with other constraints that you have on measurements done in the laboratory on finite nuclei. And the main message is shown here. This is a complicated plot I will try to explain. So first of all, what is on the axis? So on the y-axis, you have the tidal polarizability, which is a property of the neutron star. It tells you how the neutron star can deform with a quadruple deformation when it's in spiraling with the companion due to the increasingly strong gravitational force. That is what you can constrain very well from gravitational waves observation. On the x-axis, you have below here the radius of a neutron star in kilometers. Neutron star you can imagine as an infinitely big nucleus, if you want. And above, you have instead the so-called neutron skin thickness of a heavy nucleus like lead. So lead has more neutrons than protons, so what happens is that the excess neutrons extend further out with respect to the proton, forming a kind of neutron skin, that's what it's called. And you can measure that in the laboratory. And here, the curve that you see here is coming from density functional theory, from this mean field approximation, so it's not an Ab Initio method, but it's still interesting to show that the two quantities are correlated, and you can combine constraints from neutron star and constraints from lead measurements, for example, and then really decide which of these points are good, which one are not. So how do you measure the neutron skin thickness? You do that with parity violating electron scattering. So basically, this is a process where you have an exchange of a photon and a Z boson. If you look at the parity asymmetry, you can also concentrate on the weak part, which is the one that is parity violating. The latter, so you measure basically by having a polarized beam, looking at different polarization, taking the difference. And this is related to the weak charge of weak form factor, I should say, which is by itself related mostly to the distribution of the neutrons, not of the protons, because the weak charge of the neutron is roughly 1 and the one of the proton is roughly 0 due to the value of the Weinberg mixing angle. So what you measure is the form factor at 1Q. After some submission, you can extract the radius. the skin radius. There are at least 2 major programs to do that, one in JLab. The experiment to measure radius is called PIREX. And there is an equivalent effort to measure calcium-48, which is called CIREX. This is not the official logo, obviously, but I like it. My kids love it. And there is also a local effort here in Mainz to measure that at the future MESA facility, which is called MREX for Mainz Radius Experiment. They're all dinosaurs, right? So and okay, these are this is the experimental front. What can we do from the theoretical point of view? So lead is a bit of a heavy nucleus, but we did recently calcium-48, which is the nucleus I showed you at the beginning of this chart. That is the merging point where various theories can compute. So what we did is we computed the proton distribution, the neutron distribution, and their difference, which is this skin, with various chiral effective field theory potentials, which are the squares and the circle. You see we get this quite a constant neutron skin value, and here we see a nice correlation. So we can put constraints on the skin. We get a neutron skin radius which is quite small, much smaller than what is predicted by density functional theory, which are these diamonds here. You see though that the 2 methods are they overlap, so there is they are compatible, but we have a smaller skin on average than they have. Only experiment will be able to tell which one is right. We also have there are first attempts to tackle lead. Lead is really a heavy nucleus, computationally much more difficult. The level of sophistication of this calculation is not comparable to the previous one, but this preliminary or very preliminary result shows that it's actually probably possible in the future to do it well, and the result is here compared to a bunch of other ways to measure. I just would like to highlight this point here, which is coming from the PIREX experiment at JLab. 2012 was the measurement. Now they're working on PIREX 2, which is supposedly going to give lower uncertainty, and also the MREX experiment is going to give lower uncertainties. Okay. Last thing I want to tell you. Yes, sure.
How is this air skin related to neutron star thickness?
Yeah, it's linearly related, this here. So these are various functionals. You can imagine them as potentials, even they are not really potentials. You solve your Schrödinger equation, and out of that you can calculate both the radius of a neutron star and the skin thickness. And they are proportional. So if the skin thickness increases, the neutron star radius increases also.
Do you assume anything about the phase of the neutron star before?
Sorry? Can you?
The core of the neutron star, does this calculation assume anything about the phase?
Yeah, I don't know. Probably something is in there. So of course this it's not telling you much what's inside the neutron star, because there you have very high densities where this approach would not work anymore. So there is some ansatz in there, and I think they don't put quarks and gluons, but I'm not sure exactly. I'm not doing this. So. But the important message is these theories here are low energy theory. They don't work at at 3-4 times saturation density. They don't work anymore. So you have to assume something about the inside of the star. So let me go to the last point I want to make, how to connect nuclear physics with particle physics. And the way, well, you can do probably other connections too, but the one that I'm looking for is the connection between nuclei and neutrinos, which are the most elusive particles. You know, there are major investments put towards measurements of properties of the neutrinos. For example, in the so-called short or long baseline neutrino experiment, 2 examples are T2K in Japan and Dune in the US, where they want to measure mixing angles of the oscillation, etc. But all these experiments, what they have is a beam of neutrino, which is a very spread out beam, is not collimated, that hits on some detector. And the detectors are made by complex nuclei. And there is nothing to do, but you really need to know how the neutrinos interact with the nuclei if you want to interpret your data correctly. And at the moment, they have a very, very crude nuclear physics modeling in there. So which means all the extraction of the data could be completely wrong because of the wrong information on nuclear physics. Another kind of effort that we are looking into is these coherent measurements, where the idea was to measure very elusive elastic neutrino scattering collision on a nucleus. And just to point out, in the future, this experiment will use argon, and Dune also uses argon. So we have argon, oxygen 16. There are two nuclei which are perfectly in reach of these methods, such as couple cluster theory, so we would like to calculate them. I think it's also an opportunity for the MAMI facility that you are going to visit soon, because any model or any theory that you are going to use for neutrino has to be first tested on electron scattering, which is the thing you can easily measure. And if what is seen here in this plot, what is shown is the relevant kinematic region of the T2K experiment, which has oxygen as a target. Here you basically see the momentum transfer, and here the energy transfer. And the color code is related to occurrences, meaning how many times this kinematics comes into the event simulators. And you see here this where is red is where it is more important. And this is a regime which is kind of around 400 MeV of momentum transfer and 100 MeV of energy transfer, which is exactly the place where MAMI could measure data and where potentially our Ab Initio theory would work. So having said that, I have only preliminary results to show to you because we are just going in this direction. We have not done much, but for the inelastic process, which is the one you're interested in, instead of doing right away oxygen or argon, which is very difficult from the nuclear structure point of view, we said, okay, let's just try to do two particles, and let's study all the kind of operators that enter into this process, I mean, this excitation operator O, which can also be derived from chiral effective field theory. And right now we are able, so these are our calculation in black, we are able to get agreement with another calculation of JLab people. And instead, if you want to go to this medium mass nuclei, such as argon, there it is quite easy for us to calculate the coherent elastic neutrino scattering, because what you need is just a form factor, the weak form factor here, which is a ground state property. So it's much easier to calculate. And here you see the cross section. It's a teeny tiny object, of course. But what you see is there are various curves overlapping here corresponding to different form factors. So we don't see any dependence on the Hamiltonian you use. And this is because it's a very low energy process where only the first part of the form factor matters, where there is no dependence on the Hamiltonian. Okay, and with that, I will conclude by saying that I think there's a lot of progress done in these Ab Initio calculations. Our theoretical work is really key to guide and support major experiments in nuclear physics and also beyond nuclear physics, as I was trying to show you. And I think it's particularly exciting because it really allows it to connect to other fields. And then I would like to thank all my collaborators, especially the young people who have worked in producing the figures and the results I showed. And of course, thank you for your attention.